Okay, so our next speaker from Politecnico di Milano is Peng Yan. He's going to be talking about SU2-COOL. So it's a fully open source framework for non-ideal compressible flow dynamics, fluid dynamic flows. So take it away, it's all yours. Just let me know if you have any issues. Yeah, go ahead.
So good morning, everyone. My name is Peng and I'm from Politecnico di Milano. The topic of my presentation is SU2-COOL, a fully open source framework for non-ideal compressible fluid dynamics flows. So firstly, I will show the motivations behind this new framework. Okay, thank you. So as we know, in fluid dynamics, the most popular equation of state is the ideal gas mode. However, this mode is not accurate in some regions. For example, if the working condition is near the critical point or the liquid vapor saturation curve. This kind of flow is called a non-ideal flow, and the flow behavior will be different. I will show some example later. So generally, the flow is thought to be ideal if the value of the compressibility factor Z is always equal to 1, or the fundamental gas derivatives of gas dynamics gamma is larger than 1. Otherwise, the flow is non-ideal. In SU2, we already have the polytropic ideal gas mode for ideal flow and van der Waals mode, Peng-Yan mode for non-ideal flow. However, if the flow is highly non-ideal, then more accurate fluid mode is required. And an example is the fluid mode provided by CoolProbe library. So hopefully, with more accurate fluid mode, we should obtain the more accurate results. The second motivation is that, so the second motivation is that we hope to obtain a fully open source framework. Although, there are some other thermophysics libraries like Probe and Fluid Probe, but they are commercial, so their use is limited. Luckily, CoolProbe is fully open source. Okay, so it's free for development. Okay, so the goal of this work is to, couple SU2 and CoolProbe in order to extend SU2 capacity for solving non-ideal flows. Here, I just give a brief introduction of what CoolProbe is. Actually, CoolProbe is an open source thermophysics library, which is written by C++, but there are some wrappers for Python, MATLAB, Excel, and so on. And it can provide, the state-of-the-art multi-parameter equation of state, okay, and the high accuracy transport properties, including the viscosity and conductivity. There are more than 100 fluids in this library, including the popular fluids like oxygen, nitrogen, or carbon dioxide. So it should satisfy the daily use. Also, it implements an efficient tabular interpolation, to accelerate the computation or reduce the computational cost. Next, I will show the code architecture, but I mainly focus on the interface between SU2 and CoolProbe. The interface consists of 3 classes. They are CoolProbe and CoolProbe viscosity and conductivity. Here, I just show one of them as an example. Okay. So if we see this flowchart, okay, so CoolProbe, obtains the thermodynamics data like the pressure and temperature from SU2, and then it will call CoolProbe library to update them. After that, the new thermodynamics data, pressure, temperature, density, and energy, entropy, even the heat capacity. The new data will be transmitted to SU2 for other computation. And similarly, these two classes, their function is to update viscosity and the conductivity by calling CoolProbe. And this is an example of the config file. So to use this new framework, we just choose the fluid mode as CoolProbe. And here, we just type the name of the fluid. Okay, for example, nitrogen, oxygen, or carbon dioxide, as we want. After that, CoolProbe will provide some useful thermodynamics information. For example, the gas constant, the critical pressure, and temperature. So we don't need to input them manually. And similarly, we just choose the viscosity and conductivity mode as CoolProbe. So the use of the new framework will be very easy. Next, to verify this new framework, we consider 3 test cases. The first one is something like the SU2 tutorial, so long ideal compressible flows in a supersonic nozzle. And this is the geometry of the nozzle. Okay. Actually, we consider 2 subcases. Okay, as you can see in this table. The name of the first case is dilute. Actually, it's the ideal flow of the nitrogen. As you can see, the value of D and gamma, the value of D is around 1 and gamma is larger than 1. The name of the second case is dense, which represents the long ideal flow of MDN. If you see the value of D, it's around 0.665, which means the flow is moderately long ideal. Okay, because later on we will consider highly long ideal flow. These 2 figures show the control of the pressure. So next we will plot the dimensionless pressure along the center line for comparison. Okay. So in the figure at left, let's see, it's a result from ideal flow of nitrogen, and the curves with black and red color represent the results obtained using the ideal gas mode and the CoolProbe library. As you can see, these 2 curves overlap with each other very much, and the discrete black asterisk represents the difference between these results. And the maximum difference is around 0.25%, which is very small. And in the figure at the right, it shows the result from the long ideal flow of MTN, and the curve with different color and fonts represents the results obtained with CoolProbe library, Compressible mode, and fluid probe library. Again, the maximum difference is around 5%, which is limited. So the first test case, shows that the new framework is reliable in the ideal and moderately long ideal flow field. The second case is monotone Mach-Lambda variation. So for a steady inviscid flow, the variation of the Mach-Lambda with respect to the density can be written as the following. Recall that, if the flow is ideal, then the capital gamma is always larger than 1. So this term should be negative everywhere. However, for long ideal flow, gamma less than 1 is possible. So this term, dm over dz, may be positive in some region. So to capture the long monotone Mach-Lambda variation, we just we design this nozzle and consider its variable conditions. So it's the fluid as mm, and the volume of D is around 0.3, which is very small, and is related to the highly long ideal flows. Okay, and this is the contour of the Mach-Lambda. In the figure at left, we plot the variation of Mach-Lambda over density along the center line. As you can see, the value is negative everywhere except in this small region in the subplot. Okay. And it's related to the decrease of Mach-Lambda in this small region. Okay. That's funny. Again, we can say that the maximum difference between, the results using CoolProbe and Compressible is larger than 10%. and we can't ignore this difference. So the second test case, shows the necessity of using CoolProp library in the highly long ideal flow field. And the last test case is the long classic object shock. I think most of us are familiar with the expansion fan and compression shocks. Okay. However, in 1971, as Thompson pointed out, if gamma is less than 0, it's possible to observe the expansion shocks. Okay. So to capture the expansion shock, we just consider this stage, this geometry. Actually, it's a supersonic flow over a wedge. And let's say the fluid in this case is MdM, and the value of this, both the value of Z and gamma are less than 1. Okay, so this is the contour of the pressure, and let's say the existence of the shock is very clear. So now, if we plot across the shock, if we plot the Mach-Lambda and pressure, so in these two figures at right, the blue line, the blue line is the gradient convergence solution, and we can find both the Mach-Lambda and the pressure decrease across the expansion shock. Okay, so in this table, we compute the post-shock density, pressure, temperature, and Mach-Lambda using different fluid mode, like Van der Waals mode, Compressible, and CoolProp library. And the last row is the maximum difference between results using CoolProp library and other fluid modes. And let's see, the difference of pressure is around 8%, and the difference of Mach-Lambda is 21%. I think it's large. It's very large. Again, the last test case shows again, it's necessary to use the fluid mode provided by CoolProp library in the highly long ideal flow field. Okay, some final remarks. Okay, so the new framework SU2-COOL is developed by coupling SU2 and CoolProp. And the data exchange between them is achieved by 3 classes. And let's see, the new framework is verified. And finally, the function of the new framework is to extend SU2 capacity for solving long ideal compressible flows, especially in the highly long ideal flow field. Okay. That's all. Thank you.
Thanks, Peng, for the talk. So I think we're going to see questions. I saw them in before come over here. Go ahead.
Thank you very much.
You're welcome.
My only question is, what is the computation of overhead in terms of cost?
So you mean
what is the additional computation of the cost?
Computational cost. Okay. So actually, we assess the computational time for the 3 test cases. So approximately, the computation is around 20 to 30 slower. Okay, if we use CoolProp library compared with the embedded. 20 to 30%. Slower, but we have no choice. But we need to call CoolProp library effort at each iteration step. So to obtain more accurate numerical results, we need more computational cost. That's the case. Thank you.
Thank you. One more here. We'll say that. Go ahead.
Hi. Thank you. I've been also been using the CoolProp fluid mode for verification with the fluid modes in the SU2. I was wondering, are you also planning to the Android with CoolProp?
To cover what?
Oh, yeah, let's repeat the question. So for those online, the question was, are you planning to couple the adjoint with, or to take the adjoint of the COOL prop library?
Actually, I don't have the plan now, but I mean, if someone is interested, I can work with people on that topic. That's it. Thank you.
So my question was along the same lines, we have all these different libraries floating around. There's a station, there's here Christopher talking about another one. So why don't we just use labels? Lookup tables.
So just to repeat the question, in case you didn't hear, we have a lot of different libraries floating around, so could we just all use lookup tables, basically?
I mean, I have no idea about that. That's a good question. I need some time to explore the. Thank you.
Maybe a comment from Nitish?
Just a comment, we should invest in just developing a tool which can just integrate different fluid models and then you also deal with that extent. Well, I think that's the most worthwhile investment in development than integrating our tools.
Well, so
Just for now.
Yeah. It's worth discussion. Yeah. Any other comment?
could you please repeat the comment again? I don't.
My comment was that we want to generate a tool which can have all the fluid models in it, and it gives out a table that accepts brackets to store fluid model. And then you can have whatever fluid you want, and it generates a table for you, and then you can accept that in SU2 in your runtime.
Okay. Yeah, just a comment. And I think we already have some table reader code available. Different teams have been using that for different purposes. So, okay, just a comment. Okay. All right. Well, let's thank the speaker, Peng, again. So thank you for your